So we open Gnumeric. This is a worksheet environment, and here we implement our algorithm stepwise. So first step is initialization, and so there we have said ME, that is mass of the electron, to be 1 unit. Then the interaction variables, we had V naught equal to, so we gave it as equal to 10 power 6. Okay, and so that is in Hartree, and A, which is the width of the box, to be equal to 1 bar. Okay, so if you want, you can write these units also. This is 1 bar. Okay, and then we said we need the step size H. So H equal to, we can choose it as 0.1 to begin with, and the factor F is equal to minus, I think, minus 1 by 2 h squared. So minus 0.5 divided by h squared. So that is, we have to put a dollar and then square it. Okay, so that completes the initialization step. The next step is the defining the potential. So define potential. So for defining potential, we need the x vector. So x is 0, then this is equal to the previous value plus step size. So again, be careful because step size is always fixed, so therefore we use dollar. Now once that is there, then we can pull it up to 1. Okay, so format column row height autofit height. Okay, so once we got x, then we can generate the V potential. So potential is equal to basically V naught at 0 and at also 1. At both ends we have V naught, and in between it's actually 0. So that's all is the potential. Now we can plot the potential and see. So here is the plot, and so we can insert that somewhere here. Okay, so you can see that it goes to 0 in between, and at both 0 and 1 it is very, very large value. So the potential is looking the way we want, and we are happy with that. Now let us generate the matrix V, A and H. So to generate V, what we will do is we will introduce an index, and we want only from 0.1 to 0.9. So let me put the index from there only. So this is called the column index. So we can put 1, 2, 3 and then just drag them. Now you can copy them, and then you can say paste special. So in paste special, choose transpose. So this will give you the column index, and this gives you the row index. So what we are doing is we are generating the V matrix. Okay, so first thing for generating V matrix is we have chosen the row index and column index. If the row index is equal to column index, it's a diagonal element, otherwise it's a non-diagonal element. So we want a diagonal matrix for V. So we give a command if. This is a if statement. It will check for a condition. So if this is equal to this, then you put this value here, whatever is the value of the potential, else put 0. Okay, so you see, for example, here 0 is there, that's why it came 0. If you put 10 here, it will come 10 there. Okay, now if you were to apply this formula towards it will give you all zeros, and you apply it towards this side. See, now you are seeing some 2 here, some 2 there, 4 there, like that, right? So what you are seeing is, say for example, this command, if you see, it is not checking whether 2 is equal to 4, it is checking whether 2 equal to 0, and then you see it is putting this 0 there actually. E12 is 2, so it is putting E12, and so that is the confusion. So that means we should be careful about the way we want that this index should remain same. That means E should remain same at all times when we pull the formula. So there should be a dollar on this. Similarly, we want that this column index should remain same when we are using the formula. So there should have been a dollar on 10. And similarly, we want that these values should remain always here only. That means there should be a dollar on B. So that was a mistake. So now you see here, if you apply this, now you will find that you will have only values. We don't have all these non-diagonal values. Everything goes to 0. Now if you change anywhere, it should accordingly reflect in the diagonal element there. Okay. So in this particular case, because we have all of them to be 0, so it's almost actually like a 0 matrix. Okay. And of course, if you want, we can always give a uniformly a shift by 10 units or something like that. Then you can see 10s coming all along. Okay. Right. So this is the step 1. That is, we generated the V matrix. So the next step is to generate the A matrix. So for that, what we will do is, we will let us copy this as it is and then paste it in a new sheet, and here now we will call this as A matrix. Now A matrix is always constant, right? See, now right now this is obviously because that it has changed, therefore it has given some other value, so we have to change this now. So we can delete it. We have got the row index and we have got the column index. Now A matrix is a little more complicated. If this is equal to this, but now you know what we have to do. There should be a dollar on B and there should be a dollar on 2, right? So that the index will not change as you go down. It should always remain along B, and as you go rightwards, it should always remain along this particular second column only. Okay, second row only. So these two are equal, then we put a -2, else we put a 0. Okay, so let us just try to understand this right now initially. So you can see that we will get a diagonal matrix with -2 along the diagonal, if we are right. See, so we have got all -2s along the diagonal. Now what we need to get is, we need to get a +1 along this off diagonal and +1 along this off diagonal. So for that, what we have to do is, we have to further change. So it is not 0 alone. Further, one more if condition you have to put. So if this is equal to this +1, okay, so there should be again dollar, and there should be a dollar here. Okay, so you see, when it goes from C1 to this is right now C2, it will become next D2 when you pull it this side. So D2 +1. D2 +1 is D2 +1, no, D2 -1 it should be, right? D2 -1. 2 -1 will be equal to 1. Then it should be 1. 2 -1 should be equal to 1. Okay, C2 -1. If B3 is equal to C2 -1, so C2 -1 here it will not satisfy, but in the next step it will satisfy. So then you should have a 1, else we should have a 0, and of course you should have another. So now let us see if that works when you go from here to here. Yeah, it became 1, right? So of course rest of them it will remain 0. Similarly, when you go downwards, okay, let us just quickly check it. You will see that you get only ones along the upper diagonal. So now you need to give another formula for the lower diagonal also. So again you go back here. Instead of putting 0, we put again another if command. So now if this +1, right? So B3 +1 B3 equal to C2 +1. Now $B. So now what happens is, when you go here, you're going to B4. So it will become B4. B4 is 2 is equal to C2. It's still in the same rows, right? C2 +1. So $2 +1. Then so 1 + 1 equal to 2, and 2 equal to 2. Then we should have 1, else we should have 0. And you put one more bracket. So we might think that, okay, we could have simply typed the values, but that is not a good way of doing, because when you have a 100 by 100 matrix, it becomes very difficult to type the values. So it's important to learn the command so that we can easily obtain what we want. So that is the matrix, but this need not be generated again and again. See, what changes from problem to problem will be only the potential matrix. So once you generate this remains. Actually, if you add more number of rows and columns, this you have to just pull the same formula. You don't need to do it again and again. So this is the A matrix. Now the A matrix is ready with us. So once we have the V matrix and A matrix, then we can easily generate the H matrix. Okay, so again you can press Ctrl V, and we already have that with us. So now we generate the H matrix. Okay, so H matrix is very easy. It is a formula that we need to give. So delete, and now here you give equal to that we go to page 1, sheet 1. So this F we have to multiply F star, then you go to sheet 2 and then choose the A matrix, then add to this the V matrix. V matrix is in sheet 1. So be careful, matrix means only the actual matrix values, not the indices. V matrix. Now you go to sheet 3. What happened? The sheet 1 into sheet 2 plus, oh, that didn't come, plus V. Okay, so now you have the formula ready. Why is that not coming? Plus sheet 1, correct. Oh, okay, sheet 1 colon, let us go and see what are the values. F11 to N19. So let us directly type it, F11 to N19. So once you give this formula, you have to press Ctrl Shift and enter. Okay, all three together. So then we will get the H matrix. So matrix operations are done like this. You have to choose the entire matrix area first and then give the formula in the formula bar. Okay, so we got the H matrix. Now let us introduce another sheet, another new sheet. Insert sheet. Okay, so in this sheet what we will do is we will calculate the eigenvalues and eigenvectors. Okay, now let us so here now we got the H matrix. We'll calculate eigenvalues and eigenvectors. Okay, so how to do that? So because there is a 9 by 9 matrix, so what we will have is we will have 9 eigenvalues, and it's a basically symmetric matrix, so we know that it will always have distinct eigenvalues, and that is from mathematics, right? So because it's a symmetric matrix, it will have n distinct eigenvalues. So 9 by 9 matrix with 9 distinct eigenvalues it will have. So 9 eigenvalues will come in the first row, and for each eigenvalue the corresponding eigenvector will be 1 by 9. So we need actually one more row. Okay, so it should be 10 rows by 9 columns. So now you choose this entire region and then go here in the formula bar and say equal to EIGEN, eigen of. Now go to sheet 3 where our H matrix is and choose that entire. Okay, and then so yeah, it's, I don't know why that is not coming. Sheet 3, from sheet 3 we want to copy this. No problem. What we'll do is we'll just copy this. It's not staying back for whatever reason, I don't know. Previously it used to stay. It's coming back here. So say Ctrl V from sheet 3, right, and then press bracket close. So you can see sheet 3 colon C3 to K11. We can type it also. Okay, now Control Shift and enter. So we got the entire thing. Now what we can do is we can reduce the format the cells. Okay, you can right click and say format cells, you can choose number and keep only 2 decimal places and apply, say OK, and then what you do is you format column auto fit width, so it looks more easy to see now, right? So these are the eigenvalues here. The first row is the energy eigenvalues, but this is the lowest state, then the next one. So this is actually for n equal to 1, 2, 3, 4, like that up to 9. Okay, now so we have to match this with the expected eigenvalues. So what are the expected eigenvalues? We have the formula En equal to n squared, right, pi squared into h cross squared, which is 1, divided by 2 star m is m equal to 1, so a squared, right? So in this case, we have n squared pi squared by 2a squared. Okay, so what we will do is we will now give this formula. So first what we'll do is we'll generate n. So n equal to, so this is 9, 8, 7, like that. So it should go downwards. So you can pull this and you'll go up to 1. Now you can give the formula here. Formula is equal to n squared star pi squared divided by 2a squared. So divided by 2. A is 1, so 2. Okay, and we can again format this cell, reduce the number of decimal places to only 2, so that it looks more easy. Okay, and now we can use the formula across. Okay, so what we got is 4.89, 4.93. So we can calculate the percentage error if we want, so that we can see how good are our values. So percentage error is basically absolute value of this minus this divided by this. Okay, and into 100 if we do, we'll get the percentage error. So this is a very large error, 51% error. Okay, and whereas for lower we are having little smaller error. So with step size of 0.1, we find that only the first 2 or 3 values are close to the expected values within 10% error. Okay, so that means we have to reduce the step size, and then automatically this will improve. But of course, I would like to just quickly show you that now let us generate the x values here, because we can plot the wave functions and see. So these are the x values. So x, of course, if you want to plot the x and wave function, x is 0, 0.1, 0.2. I'm not giving the step size right now, just quickly showing you that how to plot the wave function. 0.9 and 1. Now this is the first wave function psi, but this is only available between here to Control C, Control V. It's a link. So what you have to say is copy, paste special, only values as value, because that is actually a formula, na? So only as a value. And so these are the psi values, psi naught actually, psi 1 you can say, first wave function. So you have to add a 0 at both the ends, and then we can plot these two. So you can see that this is the first wave function, which is pretty good. So you can use a thing and then insert that. So the first wave function looks pretty good, but when you go to the 10th wave function, you will see that the number of points that are required for sampling are not enough. So that will not give us a very good result. So this is a very quick introduction to the various steps in the algorithm and how to implement in Gnumeric. So now obviously you will realize that if you reduce the step size, the entire thing becomes more and more difficult, but of course still it can be doable. Okay, and so it is more easy once we understand the algorithm to go and implement it in a programming language like Scilab or Python.